Hello, algebra students. Mr. Lawrence here, and today we're going to learn how to solve systems using a different method called elimination. We've already seen how we can solve by graphing, and that's pretty easy to do, except sometimes our actual solution is a bit of a mystery because we're not crossing at specific integers, and so we're kind of guessing. And sometimes our guesses are good, our estimations are good, and sometimes they're not as accurate, and there really isn't a good way on a typical graph to make them more accurate. Then, of course, we learned how to do substitution, and substitution is very powerful because it's a little bit more work, but it gets us a specific answer. Now, there's some situations where substitution is too much work, and a new method called elimination would allow us to get the answer much quickly. Not always, but sometimes. And what we're going to have to do is we're going to have to learn both methods very well, and then we can determine in which situation we should use substitution and in which situation we should use elimination. Well, I'll tell you problem number one here. If you do it by substitution, you're doing it the hard way. This one is meant to be done by elimination. Now, I know you don't know what an elimination is yet, so let me talk a little bit more about that. Think about in substitution, we solve for a variable, like maybe we solve for x. Oops, I'm not in draw mode. Maybe we solve for x, and I'm just making this up, and we got x was 4y plus 1. And then we had another equation where it said like 2x plus 3y, and that would equal, I don't know, 8. And so what we did is we would take this and we would substitute it in place of x, right? Well, in elimination, we're going to eliminate a variable. Substitution got rid of one of the variables by plugging something in its place. This elimination will actually cause a variable to disappear. Take a look at this first equation. We've got 2x plus 3y equals 10, 5x minus 3y equals 4. What do you think would happen if we added those two equations together? Adding our like terms of x, we get 2x plus 5x, which is 7x. Positive 3y and a negative 3y, they cancel. They're gone. They're eliminated. And 10 plus 4 is 14. Now, some of you went, oh, wow, that's so cool. I'm always going to do it by elimination. Hold your horses, all right? Or porcupines or skunks or whatever you happen to be riding right now. I'm going to divide by 7, and I'm going to get that x equals 2. Now, just like in elimination, we have to go back and figure out why. So we're going to substitute this 2 into one of the equations in place of x. I'm thinking that I'll do it in the top equation, so I'm going to have 2, and that'll be times 2, y times 2, because x is 2, that's why I did it in blue, plus 3y equals 10. I could have substituted it into the other equation, but I thought this one would be the easier of the two. Personal preference, really. 4 plus 3y equals 10, and now I'm ready to subtract 4 from both sides. I'll get 3y equals 6. I'll divide by 3, and I'll get y equals 2. So therefore, these two lines intersect at the point 2, 2. I know a lot of you go, no, I don't care what you say, Mr. Lawrence, elimination is easier. When I was your age, I thought the same way. And I used to get a fair number of problems wrong because there are some problems where it's smarter to do elimination. There's other problems where it's smarter to do substitution. Now, problem number 2 here, you notice there's not a positive 3y and a negative 3y. There's not a negative 7x and a positive 7x. Some of you might be going, hey, we should do substitution. And that might be a good idea, but I'm actually going to do it by elimination so that you can see how it works. Okay, so I don't have any coefficients that match with opposite signs, inverse signs, do I? But if what would happen if I multiplied the second equation by negative 3, and then I'm going to multiply the 3 by negative 3. And when I do this, I'm going to get 3x plus 4y equals 12. And then my second equation becomes negative 3x minus 9y. and that's going to equal negative 9. Oh, look at that. Those match. I'm ready to add my two equations together. All right, those will cancel. I'll get a negative 5y and a 3. I'll divide by 5, and I'll get that y is equal to negative, oop, divide by negative 5, excuse me, negative 3/5. Okay, I think it might be easiest for me to go ahead and solve for x in the second equation, the original second equation. By the way, for the record, I could have solved it in a couple, plus substituted in this equation. I could have done it in this equation, which is the one I'm talking about doing before I multiplied by 3, but I also could have done it in this one. If for some reason one of those looks easier to you, it is totally okay to do that. Usually the best choice will be one of the two original equations, but not always. All right, so I'm going to take that second equation. I'm going to have x plus 3, and that 3 is going to be multiplied by, I'll tell you what, I'm going to go with a decimal here, negative 0.6. That's what 3/5 is, and that'll equal 12. No, that'll equal 3. Excuse me, I looked in the wrong place. I'm going to be using this equation here. Be careful of those mistakes. So I'm going to get x minus 1 and 8 tenths. Notice I didn't use a calculator because I know 6 times 3 is 18 without even thinking about it. Well, 6/10 times 3 is the same answer, only 1 and 8 tenths. What do you think? 0.06, 600ths times 3 is going to end up being, well, it's going to be 0.18. If you're not sure how I'm doing that, come see me. I would love to show you. All right, getting x alone, I'm going to get 4 and 8 tenths. All right, or 4 and 4/5 is the same as 4 and 8 tenths. So if I'm going fraction in my answer, I'm going to put down 4 and 4/5, negative 3/5. Okay. Or if you wanted to go decimal, you could have told me 4 and 8 tenths, and then negative 0 and 6/10, like that. I won't give you too hard a time about going decimal on some of these because the numbers start to get ugly. You've even seen me using a calculator a little more than normal. That's just because some of the numbers are very, very ugly. Okay, now before we go on, let's talk about what it is we're doing. We're trying to create a situation where we have two variables that have identical coefficients but um, inverse operations, like a positive 3x and a negative 3x, or a negative 12y and a positive 12y. And if we can do that, then we're able to add the two equations together to eliminate them. Now, this doesn't just work on linear equations. It can work on a mixture. And here in problem 3, I have a quadratic and a linear equation. And we're going to expect two answers because of the quadratic. The line will probably intersect the quadratic twice. Doesn't have to. Could be a situation where it doesn't intersect it at all. It could be a situation where it intersects it only once. But we're not really going to run into those situations until we deal more with quadratics later on. So, what do you think would be the easiest thing to eliminate? Well, you notice both y's have a coefficient of 1. If I just multiply one of those equations by negative 1, I could add them together and my y's would be eliminated. So let's multiply the bottom equation by 1, because I know I'm going to end up with a quadratic by negative 1. I'm sorry, not by 1. And when I do that, I should get a nice quadratic that'll be factorable. Now, don't try to make up your own equations to practice this, because it's not going to work. All right, there are a lot of quadratics that have solutions but aren't factorable, and that could prove to be a big problem for you. Now, pay attention to how I wrote the second equation after I distributed a negative 1. I made sure to put the like terms under each other. Okay, so I didn't accidentally combine things that weren't like. All right, so now I'm going to add these two equations together. And when I do, the y's are going to cancel, and I have to put the 0 in because there's no other numbers or variables on that side of the equation. The x squared didn't combine with anybody. He comes down. I'm going to get a negative 6x and a positive 8. Okay, so now I have an equation that is definitely factorable. I need two factors of 8 that are going to add to get negative 6. Well, I'm thinking a negative 2 and a negative 4. If I multiply them, I get positive 8. And hopefully some of you are starting to see that when the lead coefficient is 1, we can factor just like this. It's a little shortcut. If you don't see it, that's okay. You can do it the grouping method. But if this works when the lead coefficient is 1. Okay, anyway, so if I solve this, I'm going to get x equals 2, and x is going to equal 4. So I have two possible answers. Now, I think to get my y variable, the easiest equation is going to be this original one because y is alone, and there's not that many computations involved. So what is it? Y equals 7x minus 3. So for 2, I'm going to write y, let's get in a pen mode. So I'm going to write y equals 7 times 2 minus 3. And then the other one will be y equals 7 times 4 minus 3. Now I know a lot of you can do this stuff in your head, but at least show me the setup of the problem. Don't just give me an answer. Because if you make a mistake, I can't give any credit for it. 7 times 2 is 14, minus 3 is 11. And then over here, 28 minus 3 is 25. So the two places where these intersect are at 211 and at 425. Okay, let's look at one more example by elimination. This is a quadratic and a linear, but it doesn't look like it quite matches up. But you see how I have a positive 10x here and a positive 10x there? I'm not going to try to multiply by negative 1. My terms are kind of out of order. They don't match. I have a y, then an equals. Now I can't say about x squared because there's no x squared in the other equation. But I have y on one side, the x and the constant on the other. On this one, I'm in standard form. So I'll tell you what I'm going to do. I'm going to convert this second equation so that it looks more like the first equation where y is alone on one side and then x and the constant are together. So I'm rewriting the first equation. And now to get that 10x to the other side, I would subtract it, right? All right. And I'll write that answer in red. It's going to be 2y alone on the left-hand side because those canceled, right? Equals, I'm going to have a negative 10x and then a negative 30. And, that's not going to work. Because when I do that, I'm going to have y's and x squareds. And I don't think I know how to solve y's and x squared. So, oh man, that's just no good. Oh, I'm going to have to change my approach. So let me see here. Let me get rid of all this. And I guess I'm going to be forced, since I have a quadratic, and I'm going to be forced to get this second equation in slope y-intercept form and do it very much like problem number 3. So I will subtract 10x from both sides like I did. So minus 10x and minus 10x. And that will yield the equation 2y equals negative 10x minus 30. And then I'm going to divide by 2. And remember, I have to do it to all the terms. And so I'll get y equals negative 5x minus 15. Now I'm going to take time and multiply through by -1 to this blue equation. That'll change all three signs just like that, multiplying through by -1. Now my second equation, or my first equation I should say, is going to be y equals x squared plus 10x, and that's going to be plus 6, right? Okay, and I'm getting worried. I wonder if I have one that's not going to be solvable. It's okay if that happens. All right, let's see. These are going to cancel. I'm going to get a 0. I get x squared plus 15x plus 21. So, let me think here. I need two factors of 21 that add up to 15. I don't believe I know any. So for right now, um, there's no solution. And I'm going to put it in parentheses yet, because soon we're going to learn something called the quadratic formula, which will allow us to really determine if this has a solution or not. Okay, so the trick is to manipulate one of the equations, sometimes both, and if you hear me pausing, that's because the keeper of Blue Bunny has just crawled up on my lap. He's waking up early, and now he's in a cuddling mood, so I'm going to have to wrap up this video. But remember, we're going to manipulate one of the equations, usually one, but tomorrow we'll do some where we have to manipulate both, so that the coefficients on one of the variables are identical except for their signs. And when we do that, we can add the equations together, thereby eliminating that variable. All right, that's enough. The blue bunny keeper wants to cuddle, and mommy's not here, so I will say good night, everybody.